This is a video for KIG2018. So in this video, we'll be learning about the reacting mixtures and combustion. This this slides is taken from the textbook made by Moran, Shapiro, Boitner, and Bailey. So first of all, is mastering the combustion concepts. First is the reaction modeling. Develop balanced stoichiometric equations for hydrocarbon fuels using conservation of mass. System analysis. Apply energy and entropy rate balances to determine flame temperatures and heating values. The exergy accounting. Calculate chemical exergy and define exergetic efficiency for modern power systems. The resource management, determine the location and magnitudes of exergy destruction to renewable sources. So the first part, the chemical foundations. First, we have to look at the combustible fuel elements. Combustion is the rapid oxidation of fuel, releasing chemical energy. Three primary combustible elements dominate common fuels are carbon, reacting with oxygen to get carbon dioxide, hydrogen reacting with oxygen to get water, and sulfur reacting with sulfur dioxide to get reacting with oxygen to get sulfur dioxide. To note, oxygen plays an important role in the combustion reaction. So modeling the atmospheric air, there's about 21% of oxygen in our atmosphere, and and nitrogen dominates by 79%. The molar ratio calculation in combusting modeling, nitrogen is lumped together with oxygen. For every 1 mole of oxygen, we must account for 3.76 moles of N2. The molecular weight of a dry air is approximately 28.97. So the air-fuel ratio, or AF, this ratio helps us to determine whether a combustion process is lean, which is excess in air, or rich, which is excess in fuel. The molar basis, as we can see here, is that AF is equals to the N of air over the N of fuel. While the mass basis, we compare the mass, as you can see here in the formula, AF is equals to the mass of air over the mass of fuel. And from these formulas, we can make that AF of mass is equals to AF for molar times the mass times the M air over the M of fuel. So now we'll go to the second part, which is the thermal balances. The enthalpy of formation, FHFO. Standard tables are arbitrary datums that don't cancel in reactions. We use the enthalpy formation to assign absolute values. So reference state that we use 298.15 Kelvin at 1 atmospheric pressure. And stable elements enthalpy assigned as 0, which is oxygen O2, nitrogen N2, carbon C, and hydrogen H2. We can refer to the formula right here. Now the heating values of fuels, or LHV over HHV, we can see that each reactant has a different value of heating values. We can see that the methane HHV has a 55,510, while the methane LHV has a 50,020 kilojoule per kilogram. The HHV is the liquid water in products, while the LHV is water vapor in products. The adiabatic flame temperature. The temperature reaches by combustion products if no heat is lost to the environment. So for maximum TP occurs with the theoretical amount of air. Excess air acts as a thermal ballast, lowering the final temperature. The absolute entropy and the third law datum. Entropy of a pure crystalline substance is 0 at 0 Kelvin. This is where the particles have no more energy to vibrate, hence they are static at their own place. Values relative to this are absolute entropy. For component in a mixture, we can refer the formula as such. The third part, exergy analysis. Exergy is the property of a value. The energy is always conserved, which is the first law of thermodynamics, while exergy is destroyed by irreversibilities, obeying the second law of thermodynamics. Exergy is the maximum theoretical work obtained as a system reaches equilibrium with its environment. It represents the economic value of fuels like natural gas, coal, and oil. 40 to 70% of typical exergy efficiency for modern combustion system. So the total flow exergy breakdown. In reacting systems, we must account for composition differences between the system and the reference environment. Here's the formula we can see here. The exergetic efficiency, the engine, system performance. Exergetic efficiency gauges how well fuel exergy is converted to useful power. Useful power, you can see the formula as such. The work divided with N and E. For a typical 50 horsepower engine, it consumes about 1.98 times 10 to the power of negative 33 kilograms per second of fuel. So we can say that the efficiency is around 40%. Standard chemical exergy, model 2. So we can see here the substance like hydrogen, methane, octane, ethanol, each has a different ECH and has a different value of ECH and ECH over LHV, which is the mass basis. Do you note these values are obtained at 298.15 Kelvin and at a 1 atmospheric pressure. So now we'll be evaluating the chemical exergy. If the chemical exergy is unknown, it can be derived from the Gibbs function of formation for its primary components, O2, CO2, H2O. You can refer to the information as such. Now, the reference environment. The chemical exergy magnitude is highly dependent on the mole fractions of components in the Earth's atmosphere. At T0, which around 298.15 Kelvin, the oxygen is about 20.35%, carbon dioxide is around 0.03%, water in gas in vapor is around 3.12%, while nitrogen gas is 75.67%. Exergy is derived from the expansion work obtained as substance goes from pressure P0 to its environmental partial pressure. Ethanol, now we will be comparing ethanol and gasoline. On a mass basis, the chemical exergy of ethanol is about 2/3 of a gas of that of a gasoline. This results in a lower fuel mileage while using blends such as E85, which is 85% ethanol. So we can compare the exergy of both ethanol and octane. We can see that the octane has a much higher exergy value compared to ethanol, around 47,390 kilojoule per kilogram, while ethanol only has 29,470 kilojoule per kilogram. So that is all for me. Thank you.